So I want to do a few quick examples of finding the rank of a matrix. And what I'm going to do is I'm going to start with giving you two matrices that are already in row echelon form, and that makes it super easy to find the rank because the rank is just the number of pivots that we're going to have, or the number of, to say it another way, the number of leading ones that we're going to have in our row echelon form. So for example A, so looking here for example A, what we're going to do is we're going to have one, two leading ones, and that means that simply the rank of A is 2. There's really not much more to say there. You can compute the rank of the column space or the rank of the row space, and what you would get would be a subspace of dimension 2. Um, Likewise, if we were to look at example B, and if we were to look at these terms, we would have, let's see, 1, 2, 3 pivots, 3 leading ones. That means that the rank of A is going to be 3. Okay, so if you have a matrix that's in row echelon form, finding the rank is easy. The reason why this works, in something that I just kind of glossed over, but the reason why this is the reason why this method works of just finding the number of pivots is that reducing a matrix using row operations, which is what we've been accustomed to, preserves the rank. So it turns out that if you look at the rank of a matrix and then you perform an elementary row operation to that matrix, the new matrix that you get and the old matrix that you started with will have the same rank. So you can do these operations over and over. And that's why this method works of just looking at the number of pivots or the number of leading ones of a matrix A. The final thing I want to say here in these examples is look at this last matrix. Right, we have this matrix 1, 4, 2, 3, 1, 2, 4, 5, 5. It turns out that the determinant of A is going to be minus 11. And the determinant actually tells us three things that'll be useful for determining the rank. Okay, so we'll figure out what the rank is in a second. But if I have a determinant of, if I have a non-zero determinant, I don't actually care that it's minus 11 other than the fact that it's non-zero. If I have a non-zero determinant, that means that the set of vectors that we're looking at, say these could be column vectors, those are going to be linearly independent and they're going to span R3 because of what we talked about in the basis videos, right? If the determinant is non-zero. So that already tells you that it's going to be a three-dimensional set. So it's basically a spanning set. These columns are a spanning set of R3. So it's going to be a three-dimensional set. Likewise, if we were to look at the rows, 1, 4, 2, 3, 1, 2, and 4, 5, 5, again, the row rank would be 3, okay? Because again, by the same reasoning, we would have a spanning set of R3. In this case, just thinking of R3 as row vectors. But the final thing that I think is very useful to remember is that, remember that we said that the determinant of a matrix is non-zero if and only if that matrix in reduced row echelon form is the identity. So what this tells us is that we can perform some row operations and we can turn this matrix A into the identity after a certain number of however many, 2, 3, 4, 5, 6 row operations, whatever it is. And how many pivots are there in the multiplicative? How many pivots or how many leading ones are there in the identity? Well, there's 3, right? So that's another way that you can kind of get at the rank of a matrix. If it's squares, you can look at its determinant.